Good day everyone, welcome to Lesson 8. We are continuing your learnings from Lesson 7, which tackled the basics of performing material balances with chemical reaction. I have also introduced to you from Lesson 7 the method of the extent of reaction balances. So in this lesson, we will be extending your knowledge about the several methods you can use. So in general, we have three methods that you can use for the balances. The first is the extent of reaction balance method, and the second and the third are the species and elemental balances, which we will be discussing in this lecture. Okay, let's start with the species balance. The species balance method is heavily reliant on the law of conservation of mass, in the sense that you are performing the conservation of mass but using moles to signify chemical reactions. So the general form of the law of conservation of mass is given here. That's input plus generation minus output minus consumption equals accumulation. Now, since we are dealing with steady state processes, accumulation is 0. Therefore, we can simplify this balance as in or input plus generation is equal to output plus consumption. And you will be heavily relying on stoichiometry to finish the species balance, especially in the generation and consumption parts. Okay, next, a material balance is to be performed on each species present as long as balances obtained are independent equations. In order for me to show you how to use the species balance, let's solve this example. The chlorination of methane occurs by the following reaction. That's methane plus chlorine gas yields methyl chloride plus HCl. You are tasked to determine the product composition if the conversion of the limiting reactant is 67%. The feed composition in mole percent is given as 40% methane, 50% chlorine, and 10% nitrogen. So let me first write the given. Here we have our given. So I have listed there the reaction. So that is already a balanced equation. Okay. We're also given the conversion of the limiting reactant, which is 67%. And I have drawn the reactor with the feed and the product. So we are given the composition of the feed. And we are asked to solve for the composition of the product. So the required is product composition. In the product, we have your main products of the chemical reaction, CH3Cl and then HCl. We also have unreacted reactants, CH4 and Cl2, and we have the inert, that's the nitrogen. If you take a look at your chemical equation, nitrogen does not play any role in the chemical reaction, so it's present there as an inert. Okay, so let's label our unknowns. We have N1, N2 until N5. And then let's start the solution. So first, of course, we set our basis. The basis here is quite obvious. You're given the composition of the feed. This is a gaseous mixture, and it was stated that it's in percent by mole. So our basis is 100 moles of the feed. And coming from that basis, we can now directly solve for the composition of P using the species balance. Okay, for species balances, all we have to do is to remember the equation in plus generation is equal to out plus consumption. This is true for all steady state processes, okay, because we don't have any accumulation. So let me demonstrate this by performing this on nitrogen, because nitrogen is our inert, so it's the easiest balance we can do. So let's do the nitrogen balance. Okay, our nitrogen balance is input, which is 10 moles, plus generation. We all know that nitrogen here is inert, so it's neither being generated nor consumed. So generation in this case is 0, is equal to output, that's N5, which we don't know yet, plus consumption. So again, it's not being consumed, so its consumption is 0. From this equation, it's quite obvious that N5 is 10 moles, which should make sense because nitrogen is not being consumed nor being generated. So whatever nitrogen comes in, it should also be the nitrogen coming out. We will only have deviations for this when we are now solving for the species which are reacting. Okay? Before we go to the balances of the reacting species, let's first take a look at the conversion. So we will be applying the definition of conversion. So this is 0.67 is equal to, if you will remember, conversion is number of moles reacted over number of moles fed. So in terms of the limiting reactant, in this case, if your chemical equation is already balanced, it's 1:1:1:1. Our limiting reactant here is methane, CH4, because it has a lesser number of moles. If the coefficients of the balance equation is not 1:1:1:1, you might want to check if it's really the limiting reactant. Okay? So in this case, our limiting reactant is CH4. So the conversion is in minus out over in. So the input is 40 minus the output of CH4 is N3 over input is 40. From this equation, we can solve for N3. Okay, solving for N3, that is 40 times 0.67. And then 40 minus answer. So N3 is 13.2 moles of CH4. In our product stream, we still have 13.2 moles of CH4. So what does this mean? In the species balance, what you normally want to do is you want to get how much moles was reacted. And we can do this because we basically have already solved for this. The moles reacted is the numerator in your conversion. That is the 40 minus N3 term. So in this case, you simply subtract 40 from N3. You get 26.8 as the moles reacted. 26.8 moles CH4 reacted. So why is this important? This value of the number of moles of methane reacted will appear in all of the species balances of the reacting species. Because the number of moles of methane reacted would also be the number of moles of the product produced. No? We will just have to perform stoichiometry. So let me show you. If we perform the CH4 balance or the CH4 species balance, take a look at the equation above. Input, that's 40, plus generation. How much methane was being generated? The answer is 0 because methane is a reactant. It's not being generated, it's being consumed. Is equal to how much methane is going out? That's N3, 13.2, plus consumption. How much methane was consumed? That is your moles reacted, 26.8. And if you add 26.8 and 13.2, you get a true equality, which means that we have the correct balance and we have the correct number of moles reacted. Okay? And an easier way of doing this is your moles reacted would simply be you multiply the fractional conversion with the number of moles of the limiting reactant. In this case, the number of moles of limiting reactant is 40 moles, and you multiply that with the fractional conversion of 0.67. So 40 times 0.67. The number of moles reacted is 26.8. So you have two choices. Either you simply get in minus out, or the numerator of the definition of fractional conversion, or you multiply the fractional conversion with the number of moles of the limiting reactant in the feed. Okay? So now that we have the number of moles reacted, let's substitute that into the other balances. Let's perform the Cl2 balance. So what's your Cl2 balance? Or the chlorine balance? Inputs is 50. Generation is 0. Again, chlorine is a reactant. It's not being generated. Equals out, or output of chlorine is N4. That is the unreacted chlorine going out of the reactor. plus consumption. The question is, how much chlorine is being consumed? So you go back to the number of moles reacted. So the moles reacted is 26.8 moles of CH4. You simply have to perform stoichiometry using the balance equation. So 1 mole of methane is equivalent to 1 mole of Cl2. Therefore, the number of moles of chlorine consumed is still 26.8 moles. So you can add here 26.8. You can get the value of N4 as 50 minus 26.8. We get a value of N4 as 23.2 moles chlorine. Okay, so we're already done with N5. We already solved N4 and N3. So what's remaining is just N1 and N2. And to get N1 and N2, you simply perform the same balance. So let's have the CH3Cl balance. Okay, for CH3Cl, input is 0. There is no CH3Cl in the feed. Plus generation. How much CH3Cl was generated? That would come from the moles reacted, 26.8 moles of methane. Perform stoichiometry. The ratio from the balance equation is 1:1, so it's still 26.8 is equal to output. How much CH3Cl is going out? That is N1 plus consumption. Consumption is 0 because CH3Cl is not being consumed. It's being generated. Therefore, we have value of N1 26.8 moles CH3Cl. And then last one, we have the HCl balance. Same thing. Input is 0. Generation is still 26.8. Output is N2. And consumption is 0. Therefore, N2 is 26.8 moles HCl. And we have already completed the components of the product. So what's left now for you to do is you collect the values from N1 to N5, get the total number of moles, and then determine the percent by mass of the components. Okay, so that is how you perform species balance. A couple of quick reminders about the species balance method. This species balance method heavily relies on the balanced equation. So in this example, you might have noticed that the moles reacted remains the same for all balances. It's just 26.8 moles. So this is not true for all problems. For other problems, especially if your balance equation contains coefficients that are not 1, so let's say for example there's 2, there's 3, you have to perform stoichiometry just like what we did here to get the actual moles consumed or the moles generated. Okay, do not assume that the moles reacted is the same for all components. You have to perform stoichiometry. It just so happened that in this problem, the coefficients in the balance equation are all 1, so there's no change. Okay, another quick note is that for the species balance to work on a problem, you have to be provided with the equation, and then you have to balance the equation. If you're not provided with the chemical equation, then you cannot perform the species method. Okay, so this is just like the extent of reaction method, wherein the extent of reaction is actually the moles reacted, which is being corrected for the coefficient in the balance equation. Okay, so if you're given the balanced equation, you could either use the extent of reaction method or the species balance method. If you're not given the chemical reaction, you can use our next method, the atomic or the elemental balance method. I think this is the easiest way on how to perform a balance on such problems, no? Because if you're not given a chemical reaction, you can still use this. So let me show you. In the atomic balance method, balances are performed for individual elements instead of individual compounds. So let's say, for example, if you take a look at the example below, take a look at the chemical equation. That's methanol, CH3OH, plus oxygen yields CH2O plus H2O. If we were to perform the species balance method, you need to perform 4 balances. That is for methanol, for oxygen, for CH2O, and for H2O. If you were to perform the extent of reaction balance, that's still the same. You still have to perform 4 balances. But if you were to perform the atomic or the elemental balance in this problem, you only need to perform 3 balances for the 3 elements present. That's carbon, hydrogen, and oxygen. And we don't even need these chemical reactions. So let me show you. Formaldehyde, or the CH2O, is produced industrially by the catalytic oxidation of methanol, or CH3OH, given that chemical equation. However, a significant portion of the produced formaldehyde reacts with excess oxygen, so we have a side reaction. Assume that methanol and 100% excess oxygen are fed to a reactor. Assume a methanol conversion of 90% and a formaldehyde yield of 75% based on the desired equation. Determine the composition of the gas mixture leaving the reactor. So let me first list the given. Okay, here's the given of the problem. So we have our 2 equations, the desired equation and the undesired equation. Now, we don't need these equations to solve the problem if you're using the atomic balance method. Of course, if you're using the extent of reaction method or the species balance method, you will be needing the desired and the undesired equation. So let me show you the process. So we have here the reactor. Your feed is methanol and 100% excess oxygen, which tells us that oxygen is the excess reactant and methanol is the limiting reactant. Okay? In your product stream, we have your products from the desired reaction, the formaldehyde and water, and from the undesired, you have the carbon monoxide. So you don't have to list water twice because the products from the desired and the undesired reaction will come out of the same stream. So no need to separate them. And of course, in the product stream, we have the unreacted methanol and unreacted oxygen. So let's label them as N1 to N5. Okay, next, solution. We start with the basis. In this case, there's only one sensible basis, which is we assume the amount of the methanol. So why is that? If I have a basis of methanol, let's say for example, my basis is 100 moles of methanol in F, what that allows us to do is we can actually solve for the amount of oxygen being fed because the percent excess oxygen is given. Okay, that's the only basis we can do for this problem. So let's begin by determining how much oxygen is being fed to the process. We first determine the number of moles of oxygen theoretical. If you would go back to the previous lesson, we need to solve for the NO2 theo, or the number of moles theoretical, for us to be able to determine the number of moles of oxygen fed coming from the percent excess. So here's how we solve it. We start with the number of moles of methanol, and then you perform stoichiometry. By the way, our 2 equations are already balanced. And if you are talking of the theoretical number of moles, you always take a look at the desired equation only. Okay? So for the theoretical amount, we only consider the desired equation. So in the desired equation, 2 moles of methanol is equivalent to 1 mole of oxygen. So we now have the number of moles of oxygen theoretical, which is 50 moles O2 theo. Next, so how do we use that? We use that in the definition of the percent excess. If you will remember, the percent excess is defined as the number of moles of oxygen fed minus the number of moles of oxygen theoretical over the number of moles of oxygen theoretical. So that is fed minus theo all over theo times, of course, times 100%. So let me carry this here. Our percent excess oxygen is 100%, so that is 1. is equal to NO2 fed minus a Theo of 50 over Theo 50. We can get NO2 fed as 100 moles. So therefore, in the feed, we have 100 moles of methanol, which is our basis. And through the given percent excess, we have determined that the oxygen fed is also 100 moles. Now we can start with the balances. By the way, before that, we have to consider the definitions of the conversion and the yield. Let's first start with the conversion. So conversion is moles reacted over moles fed of the limiting reactant. In this case, that is the methanol. So that is the amount of methanol coming in minus out over in. So the methanol coming in is 100. The methanol coming out is N4 over the methanol coming in 100. From this, we can get N4 as, that is 100 times 0.9 and then 100 minus 90, which is 10. So that means that we have 10 moles of methanol in the product. So we're done with N4. Next, we consider the yield. So how do you define yield? So from general chemistry, yield is, or percent yield is actual yield over theoretical yield. So the yield always pertains to the product. In this case, it pertains to the desired product. And the desired product is formaldehyde or CH2O. So the actual yield or the actual output of the process for formaldehyde is N1 because that is the amount of formaldehyde that is exiting the process over the theoretical yield. So how much theoretically should be formed? That is also based on the NO2 Theo. Let's first solve for the number of moles of CH2O Theo. We start with 100 moles of the CH3OH. Again, remember, whenever we are talking about the theoretical number of moles or the theoretical yield of a substance, no? We are always considering the desired equation only, and we are considering complete reaction for the Theo only. Okay, so considering the desired equation, our coefficients are, there are 2 moles of CH3OH per 2 moles of CH2O. So that tells us that the theoretical yield or the theoretical number of moles of CH2O is 100 moles. So going back to the yield, this is 0.75 equals N1 or the actual yield over the theoretical yield of 100. We get a value of N1 that is 75 moles CH2O. So we now have N1 and N4. So those were the information given to us by the fractional conversion and the yield. So now that we have exhausted our given, we need to find the values of N2, N3, and N5, and here is where the atomic balances would come in. Okay, as I have mentioned earlier, the atomic balances are, or the concept behind atomic balances is you are just balancing the number of moles of a given element coming in to the number of moles of the given element coming out. So we are just counting the elements and not the compounds themselves. So let's start with the carbon balance or C balance. So this is just as easy as counting how many atoms or how many carbon is there in a given compound and multiplying that with the amounts of that compound. So first, in your feed, the only carbon source is methanol, and there is only 1 carbon in methanol. So we write that as 1 carbon multiplied by the amount of methanol, which is 100 moles. That is your input, equals your carbon in the output. So carbon appears in N1, N3, and N4. So you should have 3 terms on the other side of your carbon balance. So first, N1. In N1, there is 1 carbon, so we write that as 1 times the value of N1. So let me first just write N1 here, and then we will just substitute later. So that is 1 times N1 because there's only 1 carbon in N1. Next is N3. There's also 1 mole of carbon, so that's plus 1 N3. Plus in N4, there's also 1 N4. So it's basically saying that 100 is equal to N1 plus N3 plus N4. So let's substitute your known values. We were able to find N1, that's 75. N3 is still unknown. N4 is 10. So we can now solve for N3 as 100 minus 75 minus 10, which is 15 moles of CO. See, we now have the value of N3 just coming from the carbon balance. So we have 2 remaining balances. Let's go for the hydrogen balance. It's the same process. You take a look at your feed. Hydrogen only comes from methanol. And how many atoms of hydrogen are in methanol? You have 4. So that is 4 times the amount of methanol, which is 100, is equal to all of the hydrogen in the product. So in N1, you have 2. So that is 2 times N1. Next, in N2, you also have 2. So that is 2 N2. In N3, you don't have hydrogen. And in N4, you also have 4. So that's plus 4 N4. And we substitute the value. So that is 4 times 100 is equal to 2 times N1 is 75. N2 is unknown. And then N4 is 10. We can now solve for N2. Okay, so that is 400 minus 2 times 75 is 150 minus 4 times 10 is 40 divided by 2. So N2 is 105 moles. We have 105 moles of H2O. Okay, and so we now have N2. Last is N5. We have the 3 balances for the 3 atoms, carbon, hydrogen, the one remaining is oxygen. So let's perform the oxygen balance. So let me move a little bit. Okay, so for your oxygen balance, input, we have 1 oxygen on methanol, so that is 1 times 100, plus you have O2, that is 2 times 100, is equal to, in your products, 1 N1 plus N2 plus N3 plus N4 plus 2 N5. So we have 5 terms on your output side because all of your products contain oxygen. So we now have the values of N1, N2, N3, and N4. The only unknown in this oxygen balance is N5. So if you can substitute those values, we can solve for N5. So what do we have? We have 100 plus 200 minus N1. What's N1? 75. Minus N2. N2 is 105. Minus N3. N3 is 15 minus N4. N4 is 10 divided by 2. So we say that N5 is 47.5 moles oxygen. So there we have it. We have found all of the values of the components of your product by using the atomic balance method. The atomic balance method, I think, is the easiest to remember and the easiest to perform since we did not rely on the balanced equation. Although, you have to learn all of the 3 methods because in the exam, you will be asked to solve a specific problem using a specific method. Okay, so you have to remember the extent of reaction balance, the species balance, and the atomic balance. But moving forward, you are free to use the atomic balance method. Okay, so that is the atomic. Of course, this problem is not yet finished, so I will be leaving this up to you, no? We are asked for the product composition, so your output here should be percent by mole or mole fraction. So you simply gather all of the values from N1 to N5 and then determine their mole fractions. Okay, let's proceed. Okay, so this remaining few examples will be your worksheet number 6. So the worksheet number 5 are the 3 problems from lesson 7. Worksheet number 6 are the 3 problems from lesson 8. So these are 3 problems. So what I want you to do with here is I want you to perform the 3 balances for every problem if it is possible. So let's take a look at number 1. In an experimental cracking of octane, the product has the following composition. So you're given the composition. So cracking is the process of reacting long hydrocarbon chains with hydrogen gas to produce hydrocarbons of shorter lengths. Determine the molar ratio of hydrogen gas consumed to octane reacted. So you're not given the balance equation, and in fact, there is no chemical equation here because it's a very complicated process. But what we know is our reactants are octane and hydrogen gas. And our products are given C3H8, C4H10, and C5H12. So in this case, you cannot perform the species balance and the extent of reaction balance because there's no chemical equation given. So for number 1, you can only perform the atomic balance method. So perform the atomic balance method for number 1. For number 2, we are given the chemical equation. So I expect you to perform the 3 methods and then compare your answers. Your answers should be the same. And finally, for number 3, you're also given a chemical equation. So you perform the 3 methods here and then compare your answers from those 3 methods. And they should be the same. If ever you have difficulties answering these problems, you could always message me for some enlightenment. And this is already your review for our upcoming exam number 2. Your exam number 2 will be next Saturday, so that is July 18. Again, exam number 2 is July 18 during our period, so that is 1:30 to 4:30. Okay, it's still on Blackboard. And the coverage of the exam will be the recycle, bypass, and purge for non-reactive processes, and this one, the material balance with chemical reactions. Okay, I repeat, if you have questions on this lecture or in any other lecture, don't hesitate to message me. And I will try my best to reply as soon as possible. You can message me through Messenger for faster replies. That's it for this lesson. I hope you have learned something. And as always, keep safe.